Okay, here's the randomization test video example that I promised. This is number 1 from the online quiz. So what's going on here? We have a control group and a soap group, and then we're counting the number of bacteria colonies present in each dish that were either given soap or given just water. That's what the control is, just water. And so both dishes were exposed to bacteria, E. coli bacteria, and the idea is that we want to see, did the soap have any effect on the E. coli bacteria? Did it help it grow, or did it kill it? We don't know. We're just trying to see if the mean number of bacterial colonies in each of the groups is different from each other. Okay, so when you read the question, notice it's asking if the average number of bacterial colonies in each group is different. Okay, so we're asked to calculate the p-value for the test, right? So we can figure out, the mean number of bacterial colonies for the control group was 41 colonies, and the mean for the soap group was 33, and that's an 8 colony difference in the average. 41 minus 33 is 8. However, what we need to know is that significant, right? So did lining up in the soap group, did that have an effect on the number of bacteria colonies that were present? Was it important that soap was given to these two groups, or was it just random? By chance, we just happened to have found, that there was this 30 and 36 number of bacteria colonies in those two dishes. Was it just random that those two dishes happened to be on average less than the control dishes, or was it actually due to the soap? Okay, so we'll use p-value to calculate this, and we're using the randomization test. So let's define what a p-value is, and then it'll be clear what it is we need to do. So p-value is the probability that a test statistic is at least as extreme. Okay, that's a really important part. So probability that a test statistic. So a test statistic can be anything. In the t-test, for example, it's that TS. Right? In the Wilcoxon-Mann-Whitney test that we talked about, and is also covered in this chapter, that's that US, right? So a test statistic. In the randomization test, the test statistic is actually just the difference in the means, okay? So our observed test statistic was 8. So the probability that the test statistic is at least as extreme as the observed test statistic under the conditions that the null hypothesis is true. Okay, so first step in the randomization test is to come up with the distribution of the test statistic under the null hypothesis. So under the null hypothesis, it wouldn't matter if if a petri dish had been assigned to control or soap. It wouldn't have mattered. So the group doesn't matter at all. So under the null hypothesis, these 4 data points could have been randomly grouped into any, either control or soap, right? Those 4 data points could have been anywhere if the null hypothesis was true. Okay, so p-value, we're calculating some sort of probability given that the null hypothesis was true. So first step is to find the distribution of the test statistic under the assumption that the null hypothesis is true. So if the null hypothesis is true, these 56 could have been over here, and 30 then would have to have been over there. Where these 4 data points lined up, being in the control group or being in the soap group, wouldn't have mattered. So we can come up with all the different permutations. Okay, so I just put them all here. So the first one, you see the 30 jumped over to the control, the 56 went over to the soap. And you just kind of come up with all the different ways you could have reorganized the data had the group not mattered, right? So under the null hypothesis, the group doesn't matter. So you just come up with all these different possibilities. Okay, and then what we came up with is a distribution for the test statistic under the null hypothesis. So the values that the test statistic can take, values of the test statistic are, so the observed value was 8, right? And then negative 18, 33, negative 8, 18, and negative 33. So those are the values that the test statistic can take under the null hypothesis. The values of the test statistic, assuming that the null is true. So all of these values, if the null is true, all these values are equally likely. Okay? Because it didn't matter. It was just random that we happened to observe this first one, 8. We could have observed any of these other ones just randomly. Okay, so to calculate our p-value, the p-value is the probability that the test statistic. Alright, so it's going to be the probability that our test statistic, which is y, I'm going to write, let's see, y bar 1, let's see. I'm going to write this, the mean 1 minus mean 2. So mean 1 is the control group's mean, and mean 2 is the SOAP group's mean. Okay, so that difference, okay, so that was the test statistic, right, is at least as extreme. So that difference is at least as extreme. So that means it needs to be at least as extreme as the observed statistic value. Alright, so 8 is the observed value. Okay, and this difference needs to be greater than or equal to 8. That's what at least as extreme means. Right? If it's less than 8, that would be that these two means are really close to each other. Remember, the whole thing is we're trying to test if those means are different. So we're trying to find the probability that it's at least as extreme. Now, it could have been negative as well. So this difference, it would have still been different had it been negative 8, then we would want it to be less than negative 8, right? So we want it to be like escaping to the the sides of the number line, so we want it to be less than negative 8 and more than positive 8. So we could just write that as we want this absolute difference. We want whatever this absolute difference is to be more than 8. Okay? So the absolute difference is more than 8. The distance from 0 is more than 8. Okay, given that the null is true. Okay, so we have the distribution of the test statistic given that the null is true, and we can find the number of times it's less than, that it's more than 8, more than or equal to 8. So every time, right? 1, 2, 3, 4, 5, 6. 6 out of 6 times is greater than or equal to 8. So the p-value equals 1. Alright, so p-value equals 1. That means that that is greater than alpha, right? Alpha, recall, alpha is the probability of rejecting the null hypothesis given that the null is true, right? Or the acceptable probabilities. Usually you define it before you start. So acceptable probability of rejecting the null hypothesis given that the null is true. So usually you set that to be pretty low, right? And then ultimately you make a decision. You say if the p-value, if you say that if the p-value is less than alpha, then you reject the null, right? In this case, you would reject the fact that that these two groups are that they have the same mean. You would say that they have a different mean if the p-value was less than alpha. Well, if the p-value is 1, that's the highest it could possibly be. Remember, probability is between 0 and 1. So in this case, we're definitely not going to be rejecting the null hypothesis. We have no evidence to say that the difference in these two groups, the mean difference is the difference of the means is anything other than 0. Okay, so we have no evidence to say that the control or the soap had any effect on the bacteria different than the control group. Okay, if we were to change this question, as opposed to it being, if we were to change this, let me rewrite this down here. Calculate the p-value for the test that the average number of bacteria colonies is less in the dishes with soap. Okay, that would make sense. I would say that the soap is killing the bacteria, and that's our hypothesis in the get-go. Okay, so the hypothesis up here would have had to have been, we have no idea if the soap is going to help the bacteria grow or not, or kill it, right? So down here we're saying, yeah, we think that the soap is going to kill it. Okay, so we want to calculate a different p-value. Okay, p-value is test dependent. So, the p-value would change in this situation. So the p-value, if we were to calculate it here, the p-value, it would be the probability that the mean in 1 minus the mean in 2 is greater than 8. Okay, and so notice that we lose the absolute value, right? And the reason for that is that if mean 1 is more than mean 2, then it's going to be greater than 8, right? And we're looking for the test statistic to be extreme, right? But if mean 1 is less than mean 2, then this difference is going to be negative, okay? And that's not what that's not what the alternative hypothesis is getting at, right? The alternative hypothesis wants us to figure out if mean 2 is actually less than mean 1. We don't want to include in our definition of what extreme means. We don't want to include the situations for when mean 1 is less than mean 2. Okay, so your definition of what an extreme is depends on what your alternative hypothesis is. So the extreme is only the range where the alternative hypothesis would be considered to be true. Okay, so the alternative hypothesis here that the mean in the second group, or the mean in the soap group, is less than the mean in the control group, that difference will be greater than our observed test statistic. Okay, so given that the null is true, so now we just go up and we still have the distribution of the test statistic, assuming that the null is true. Okay, we still have that whole distribution. We just count the number of times it's greater than or equal to 8. And so it's greater than or equal to 8 1, 2, 3 times. 3 out of the 6 times. So that's half of the time. So half of the time, it's probably, or definitely, you wouldn't define alpha to be 0.5. So, you would again decide to reject, or to fail to reject the null hypothesis, that you don't have evidence in this situation to say that the soap decreased the number of bacteria colonies than in the control group.